trying to do this in half an hour, so this is a waves test. I was like, why not? Sure. So state and explain which wave is longitudinal. B has refractions and reflection. Wait a second, this tablet's doing a bit of madness. There. The figure above clearly indicate the wavelength of wave B. So there's that one to about the wavelength, and use our show direction which point P and Q about to move as each wave moves to right. So that's going to move up, that's going to move that way. Electromagnetic waves are similar to wave A. Wave A is a transverse wave. Explain why it's important to correctly align to receive the strongest signal. EM waves, radio waves in this case, will be polarized. They're plane polarized, not just polarized, plane polarized. Therefore, you will need to align accurately or you will get a weak signal. I am going to be doing it in half an hour, quick. The figure shows triggers whether define the amplitude, maximum displacement from point of equilibrium. The wave travels to the right. Explain how the vertical displacement of a knot varies with the next complete cycle. So this will go down and up over the next half cycle, will go down, then will gradually, not half, quarter, so we'll go down, then we'll gradually get up for the next half cycle, then go down again. So it's gonna go down and then up. That won't move like that, obviously. Continuous wave with the same amplitude and frequency moves along the rope from the right and passes through the first wave. The knot becomes motionless. Explain how this could happen. A stationary wave is formed. Wave is formed. Therefore, we will have destructive. No, wait. Continuous wave of the same amplitude and frequency moves along the rope. First wave, the knot becomes motionless. Therefore, we will have destructive interference and the knot becomes a node. State one characteristic feature of a longitudinal wave. So, series of, nope, I think the characteristic feature of a longitudinal wave vibrates parallel to direction of propagation. Transverse particles vibrate perpendicular to direction of propagation. Yeah, like a revision thing, innit? Daylight passes horizontally through blah blah blah, rotating, so this is doing that. So what would the observer see? The observer would see something like that. So, with the first 90 degrees, it will be dimmer until you reach 90. Then it will increase to a maximum at 180 degrees and will go back to a 0 at 270, then max at 360 degrees. Amplitude, done that already. Other electromagnetic wave, another wave that's transverse. What other wave is transverse? On a spring. Well, stationary wave on a string, but there's also the spring one. Spring, but I don't know how to word it. It's the one where it like you move it up and down on a spring. Okay, and say one difference between transverse wave and longitudinal wave. Longitudinal needs a medium. Needs a medium. Blah blah blah. Polarized filter rotated clockwise. Oh, this is the one that I drew already. So it goes from a maximum. It looks like a demented W for someone who doesn't look like doesn't know what W looks like. So one application other than education for polarizing filters, 3D lenses enhances viewing pleasure. The diagram represents polarized wave traveling. Calculate the wavelength. So this is here to here would be the wavelength. So this is an addition one full wavelength. So that means that this would be a quarter of a wavelength. So does that mean that I need a calculator? So 0.5 equals 0.5 divided by 1.25. That means 0.4. Frequency is that. Calculate the speed. So wave speed equals frequency times wavelength. So 8.8. Phase difference between point X and point Y, giving appropriate units. Okay then, so that is phase difference. So that is 180, that is 90 plus 180 is 270. I'm pretty sure. Yeah, but that's 90, and then there's a whole wavelength. Cool. Describe how displacement of point Y varies. Goes up for the next quarter, then goes down, then goes back up because it will do that. Goes up for the next quarter wavelength, then goes down for half, then up a quarter again. Figure 1 represents a stationary wave falling on a steel string, blah blah blah. Explain why stationary waves form. So two waves go in opposite directions to one another. They conduct superposition. So they conduct superposition as they are coherent. At nodes, destructive interference. At antinodes, constructive. Perfect. The stationary wave has a frequency of that much. String PQ has a length of that much. Calculate the wave speed. So wave speed equals wavelength times frequency. 150 times 2.4. So 360. I would assume that is right. Draw the stationary wave that would be formed if it was vibrating at that many. So that is the third harmonic. So that means that would be... I would try and make these equal, but I can't. Because predicaments of like having a screen to do this on. So microwave transmitter, blah blah blah, maximum minima are formed. Okay, so microwave transmitter does that and it reflects back like that. So microwave are transmitted, reflect off plate, and travel in opposite direction, would interfere, would be coherent, and monochromatic. So would conduct superposition. So at nodes would be destructive, and at antinodes would be constructive. No energy transfer. No energy transfer. Okay. The detector is placed at a position where the intensity is at minimum. When it is moved at a distance of 144 meters, it passes through 9 maxima and reaches a minimum from starting point. So it passes through, say this is a wave, so it does that. So say it starts from here at a minima. It passes through 1 maxima, 2, 3, 4, 5, 6, 7, 8, 9. So it does actually go through here to here. And this distance is 144. So that is 1 wave, 2, 3, 4. So 114 divided by 436. I'm pretty sure. 1, 2, 1, 2, 3, 4.5. So divided by 4.5, 32. The frequency, so we know that microwaves travel at 3 times 10 to the 8 equals, the wavelength is in millimeters. That would have to be converted into meters. So that would be 32 times 1,000 times whatever. So that would be 9400 hertz. Oh, there's a lot left. Explain how station. Oh, we've done this already. Calculate the wavelength or fundal of this vibration. Okay, so stationary wave is made. Sketch the stationary wave made. So that'd be. There. So what's the wavelength? So there's 1.28. Speed of a progressive wave. So it is moving at that many hertz and at that wavelength. 1.28 times 108 is 138. And tuning a guitar, the guitar T produces an overtone that has a node 0.6 meters from bridge A. Sketch that. What? Wait, so that makes no sense. Has an overtone. So sketch the stationary wave. So 0.64 divided by 0.16 is 4. So that means there are 4 harmonics. 1, 3. Well, is the 4th harmonic. So it's that. Calculate the frequency of the overtone. Well, when tuning a guitar, the overtone is that much. And do we know what the frequency for the first one is 108, and this is the 4th harmonic, so 108 times 4, 432. Guitarist needs to raise the fundamental frequency. One way this can be achieved, so fundamental frequency equals 1 over 2L root tension over mu. He needs to raise this. That means that he has to have a lower length. Lower length. If you lower the length. When not played on the violin, the sound produces a constant fundamental many overtones. Blah blah blah. Describes the motion of X. Well, this is fundamental. This is fundamental many overtones. Stationary wave moves up and down through the point of equilibrium. So it will just move that way and we'll move up, etc. Phase relationship between X and Y. So antiphase. And that is about, well, if that's there, that's about half of that. So that's about 45 plus 90, 135. And X and Z is about in phase. And that's 45 plus 180 plus 90, 315. And that's degrees and degrees. Frequency is over times how many hertz. So the speed is about that many meters per second. So we know that the wave speed, the distance is that, and we know that that is the speed. So frequency equals wave speed equals frequency times lambda. So one wave is 160 millimeters. 160 divided by 1000, first of all, times 180. Yep. And so that is 160 over 1000 times 780 equals about 125. Perfect. Calculate the time taken for the string to move from a point of maximum displacement back to a point of zero displacement. So frequency, well, it has a speed of 125 meters per second, and maximum to minimum would be a quarter wavelength, so that would be 0.4 millimeters. The time taken to move, no, 0.4 meters. Yeah, because I just did that one. So the time taken to move 0.4 meters, with that being meters. So speed equals distance over time. So speed equals distance over time. So distance over speed, 3.2 times 10 to the minus 3. Cool. The name given to the point midway between A and C antinode. What does that keep happening then? Calculate the wavelength of the stationary wave. The distance between is that many millimeters, so that means 480 millimeters, 0.48. Calculate the frequency. The speed of a progressive wave remains about that much. So wave speed, 125 over wavelength is about 260 hertz. Two more. Figure 1 shows a stretched string on a vibrator, right hand and 2 loops. Stationary wave produced on a string. String vibrates 2 loops. So the physical conditions needed for stationary wave to form on a string coherent. So same wavelength plus frequency. Monochromatic. That also means same wavelength. And fixed phase relationship. And state how you know that the wave on the string is transverse. State how you know that the wave on the string is transverse. No compressions or refractions. Compare the amplitude and phase of the oscillator on A to B. What do you mean compare the phase and the phase? Not in phase. Or out of phase. Amplitude, both are not at max. A is more. The length is 1.2 and the speed of the transverse wave on the string is that many meters a second. Calculate the vibration frequency. So wave speed equals wavelength over 1.2. So that's about 5.2. And frequency is tripled. Frequency is tripled. So that means now there's 6 harmonics. Yeah, there's 6 harmonics now. So that means 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Well, that was easy. I did that in 20 minutes. So now we actually look up the mark scheme. It is loading. It's taking very long to load today. AQA, waves, waves mark scheme, because we have, oh, for God's sake, show on your diagram that 3 points oscillate in phase. Okay, I'm going to pretend I just didn't see that, because theoretically I did look up the mark scheme before I saw it, so that'd be uncalled for. So green, give me green. B, reflection, refraction. Oh, refractions, yeah. I should have written compressions there, but I also just said refractions or reflections. So arrow vertically upwards, arrow left, and double-ended between 2 points in phase. Pretty sure that's right. And next one, polarized. So must be in the same plane. Plane polarized. I've just said it in the same word. Done. Question 2, maximum displacement from point of equilibrium. Downwards, upwards, downwards. At the start, cycle will go down. This will gradually go up and will go down. Yep. Next. Stationary wave is formed. Superposition. Node. Stationary wave is formed. Interference and node. And waves cancel where the knot is. Allow standing wave. So destructive interference. Longitudinal waves. Particles vibrate same direction to the direction of propagation and perpendicular to the direction of propagation. Next, B, variation intensity between maximum and minimum, 2 maxima, 2 minima, and a 360-degree rotation. So I did actually write the minima, then the maxima, then the minima, then the maxima. To find the amplitude, I already got that mark before. Question 4, either water and ripple tank or slinky. Slinky. Well in. That's a bit stupid, but sure. Longitudinal waves need a medium. Yep. But you could have also had, can be polarized. Transverse waves can be polarized. So this one, see the question? It was meant to be like that. Yeah. This one, W, yep. 3D lenses, yep. You could have also had cameras, microscopes, stress analyzers. Okay, 0.4, yep. 0.88, yep. And 270. I hope. There's 90 or 450 degrees. 90 or 450 degrees. Phase difference between point X and Y. The phase difference. There's 90 degrees. There's 180 degrees. That makes 270. Fair enough. No. Wait, what am I? Nope. So describe how the displacement on point Y varies over the next half. We'll go up, then we'll turn to its original. We'll go up, and then we'll go down. Okay. Explain why stationary strings are performed. Two waves travel in opposite directions, have the same frequency, have the same amplitude. conduct superposition, accept interference, superposition, that 2 waves, opposite direction. Yep. Next one, 360. Next, a DNA looking thing with 3 things. Yep. Next, interference or superposition gets you a mark. So superposition. Reflection from metal plates. Microwaves are transmitted. Plate travel in opposite direction. Yep. Traveling in opposite directions. Maxima is destructive. Minima is destructive. Constructive is maxima. And nodes and antinodes. So no energy transfer. Superposition. Nudes will be destructive and constructive. Yep. So wavelength of the microwave, which is 32 millimeters. Yep. And it is 9 times 3, 8 times 10 to the, no. So that was 1. Oh no. Okay, then this one I have already answered. And because I got all the marks down, giving myself all the marks here. Hey, you know what? I don't think it'll make a difference, but I'm just giving myself 4, but I got 4 out of 4 on that one. So, 1 loop, nodes on each bridge. Yep. 1.28. Yep. 138. Yep. 4 antinodes. 1, 2, 3, 4. Yep. And 430 or 432. Yes. So decrease the length, increase tension or tighten string. Decrease length. Oscillate / vibrate. And goes up and down across equilibrium. Move up and down through equilibrium. Perfect. Antiphase. I got the degree wrong, but antiphase. And in phase. I also got the degree wrong, but it doesn't care because that's the part which is mentioned in bold. Okay, then 124.8. I got 125, so I just rounded, yeah. 32, 3.2 times 10 to the minus 4. Well, I'm claiming 2 because that should be a 4, idiot. Antinode, 0.48 and 260. Yes. Next, reflection, 2 waves traveling in opposite directions, have similar amplitudes, have similar frequencies, and only lose energy at the wall. So coherent has the same frequencies. But surely, okay, reflection, 2 waves traveling in the same direction, fixed phase relationship, similar amplitude, only lose a little energy. So I'm claiming 2, but I didn't write all of them. Displacement perpendicular to the rest position. The composition, state how you know. There's no compression and refraction. Displacement is perpendicular. Well, that's not the answer they put. It's still like not wrong, but A is larger. Yep. And out of phase. Yes. Then 5.2. Yeah. And then 6 loops. Yep. And that is 1 mark because I just didn't do this one for some reason. So that's 1, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 30, 30, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78. So 78 out of 7 plus 8 plus 5 plus 8 plus 7 plus 7 plus 7 plus 6 plus 9 plus 13 plus 12 equals 89. So that is 87%.